Okay. Then Yarai Shurun will talk about deeper than you think, partisan-dependent brain response. And finally, Shahar Arzy about brain coding for social structure and its distribution in Alzheimer's disease. So the idea for this session was to kind of talk about new approaches or advancing or looking at cognitive sciences from a more ecological perspective, while trying to increase ecological validity of cognitive neuroscience by various ways. So the main ways that we were thinking of how to present these, this approach was in terms of the stimuli that are used in experiments, which can be used not only for lab-based experiments, as we are all familiar with, but going into more real life or real life-like stimuli, which are more naturalistic and have higher ecological validity. And also in the behavioral repertoire, which we examine during these experiments, which we would like to advocate in favor of going beyond sitting in front of a computer, although it's very difficult and sometimes impossible. And this is enabled by various advances, both in technology, for instance, mobile neuroimaging techniques, and computer-based advances, for instance, graphics processing units, which I think Shahar will talk about, of large-scale databases. We have each 20 minutes. After each presentation, you can use the raise hand emoji to ask questions, and I'll begin with with my presentation. So I was going to talk about films and music, but I will concentrate only on music, which is an ongoing project that we started in the lab. And our interest in this project is to use a very ecological and prevalent means of that is a very part of our daily lives, which is music, and to understand how different elements of music affect cognition and specifically memory. So the main scheme of memory, as we are familiar with, is that the stages of memory start usually from sensory information that are encoded and can be consolidated into long-term memory, retrieved and reconsolidated. What we were focused on in my lab and also earlier when I was working also with Aya and Yara here in PhD, different stimuli that are on the spectrum of from lab-based memory, like for instance, learning memory for words, paired associates, etc., to real life memory, using movies as a model for real life memory, and actual real life memory, for instance, retrieval of autobiographical memory. So this can be seen as kind of going from lab to real life. Today, I would like to talk about music, and specifically about musical tension, and how musical tension, which is something that we hear a lot, but we're not necessarily aware of, how this can affect declarative memory for images. So first of all, why music? Music, first of all, as I said, is immensely prevalent. Most people listen to music either intentionally or not, almost every day, or maybe every day. And it can be processed in combination with other tasks, making it kind of easy or available for assessing the influences of music and other cognitive tasks that are done concurrently. And as we know, it induces emotions, and typically non-negative emotions, except for this guy who's crying in a Paul McCartney concert. And this is an example of a hand with goosebumps while listening to music. We know that music can induce all kinds of different types of emotion. It's very powerful. And within the music, musical elements, there's a unique and I thought very interesting feature that there's dynamics within the music that evoke. This is a citation from a prominent music researcher and composer, Leonard Meyer, who says that music can evoke a sense of abstract expectation, which awaits to be resolved into a more stable state. So many times in music, and this is known by both by composers, people who are involved in music, there are all kinds of tricks to induce emotions during by music, by raising, for instance, by raising tension and then resolving it, which is something that we know also from other cognitive domains, such as how people learn by prediction errors, or we create expectations and these expectations are met or not met, etc. So for this experiment that I'm going to show, it was led or is led by Nauras Kulzum, who's a PhD student in my lab and also a very talented musical piano player and composer. And he had the idea of testing the effects of musical elements on cognition, and specifically on memory. So when you come to talk about the effects of background music on learning and memory, there are quite a lot of research that is done and that has been done, but the findings or the conclusions are not consistent and are inconclusive. Sometimes music has been shown to enhance memory. Sometimes it has been shown to interfere with memory. And there are two main models that have been used, which are not specific necessarily to music, but are used in order to assess the effects of music. One is the cognitive capacity model raised by Daniel Kahneman, who said that incoming cues, whatever they are, if there are multiple cues, they have to compete for attention. In this sense, one would expect that background music would interfere with whatever cognitive tasks people are doing during listening to music. But on the other hand, as I mentioned earlier, music can induce prominent arousal and mood or emotions. And this can actually increase the attention that is being allocated to anything that's going on in the background. So according to the arousal mood hypothesis, music-induced emotions increase attention, and this can enable enhanced memory performance. So we kind of work in this theoretical background. What Nauras did for this experiment was compose 3 pieces on a piano, played them on a piano. And soon I'll say exactly what the tension is there, but how does one go about creating musical tension in the first place? So I'll give you just a short example of a major scale. This is a normal state of affairs, but if you want to create some sense of tension, you can do something like this. So you might have noticed that there was a delay in the last note that is involved in kind of releasing the tension that was created by not resolving the last note and going to the root note of the scale. This can, in some people, and not necessarily in all, creates a sense of kind of unease or suspense. And this can be used. This can be used not only in scales, but in the music itself. So Nauras created or composed these musical pieces, and sometimes within the music, the phrases were resolved. And technically, it's from there's a trick of doing it from the dominant 5th chord, which is a tension-invoking chord or harmonic progression, which has to be resolved in order for people to comprehend some sort of easiness in the music. So this is an example of a neutral excerpt. And this is an example of the same musical phrase, but with tension. Okay, so the only difference between them is the delay in the final transition from the dominant fifth to the root chord. And there are a lot of examples here. And these were embedded in continuous musical stimuli, which were just conveyed to the subject. So I'll show the experiment design and then go into the information. What people did, the participants came to the lab or and listened to the music while looking at a computer screen that was presented with images during the neutral musical elements, the tension-related musical elements, and the tension release, and also in silence between the music excerpts or pieces for kind of a baseline. Then 24 hours later, they came back and did a recognition memory test for the images and rated their confidence. So this is an example of musical notation, which was listened to by participants in the background during the presentation of different images in different elements of the music, which we defined. So this is the general scheme. People encoded images while listening to music. Then 24 hours later, they had a recognition test, and then they had another rating session of tension, which I'll explain in a minute, and also answered a music questionnaire related to their background of music, in background in music. You see that there are chats here, but I'll look at it after the presentation. Okay, so first of all, we wanted to validate the musical stimuli in the sense that how do we know that what we think is musical tension was in fact musical tension or induces tension? So we did this by three ways. One is by using objective measurements of acoustical measures analysis, which I'll go into in a minute. Another is by testing the physiological arousal of participants, a separate group of participants when hearing the music without going through the memory process. And another thing is by having people just rate subjectively the extent to which they felt tension during listening to excerpts from the original pieces. So first of all, going through the acoustical measurements, which is important, I think, for this session in terms of how we can go about analyzing stimuli, which we want to control for, but are nevertheless more naturalistic and continuous, like when we use movies or other things that are less controlled for in terms of cognitive lab experiments. So we use the music information retrieval framework or toolbox that can do various analysis on musical waveforms. So this is the waveform of the first musical piece that participants listened to. And you can see that we can segment, I mean, we can, the toolbox can automatically segment different features or periods within the music in terms of amplitude and changes in the musical waveform. And importantly, we can also measure the decay times from each musical element, chord or note, to the next musical element, and validate what we think is our conditions. So as I said, we had three main conditions. We had the tension condition, neutral condition, and release condition, which corresponds to the periods within the musical pieces where we presented images of different types. I mean, the images were the same type, but the thing that changed between them was the background music on top of which they were presented. So in red here, you see the times where the images were presented during tension, in blue during neutral music, and in green during the resolution of tension. And what we did is measure, for instance, the decay length of the times where different images were presented. And we see that when what we thought was the tension condition, in fact, the decay lengths where subsequently chords or melodies were resolved were longer than during neutral images or during release images. But novelty, which has to do with the abrupt changes in musical properties, was higher for the release of tension, which makes sense because those are the times where changes occur in the music from kind of a delay in music to the release of music. So this is how all the musical excerpts look like in terms of amplitude, decay, and novelty. And the other thing we did is, I see I don't have a lot of time, so I'll go fast. The physiological arousal, we showed that the tension periods evoked stronger skin conductance response than neutral images. And maybe the most important thing is the tension ratings. Tension ratings were just subjective reports of how much people seem to have felt tension during listening to different excerpts that either had tension or did not have tension. And as you see here, the average is shows that people are able to feel the tension or to perceive the tension, but there's a lot of variability. Some people feel tension, some people don't. And there's overlap between the felt tension of different excerpts. And this is important for the next, for the findings. So I'll go over the findings. What we saw in the memory test was that overall memory was superior for images presented during music versus silence in general. What we see here is D prime, that is hit rates divided by false alarms for each condition, showing that tension was on average that showed the highest memory performance, but not significantly different than neutral, whereas both of them were different than silence and were better than release. This is true also for the area under the curve, which takes into account also confidence ratings. But the interesting thing that we found is that the variability in the perception of tension, the subjective conscious perception of tension, was related to the effect that musical tension had on memory, such that the higher the perception of musical tension, the lower was the memory for pictures presented during musical tension, and vice versa. For instance, if you look here, you see that on the x-axis is the ability to perceive tension. People who were aware of the tension were, that perceived tension as such had a harder time in recognizing the images that were presented during tension, whereas if they did not perceive it, then they remembered the images presented during tension better than in the neutral stage. So there's kind of a trade-off between tension perception and subsequent memory. And this is not true for other conditions, for instance, the release of tension or tension versus silence. And in terms of 1 minute, okay, I'll just say here that in terms of musical background, maybe surprisingly, musical background was not correlated with the ability to perceive tension. This is what is shown here: musical interest, ability, listening to music. These are subjective reports in the questionnaire. And this is also shown in the literature, where musical training or ability does not necessarily correlate with tension perception or with memory. So to conclude, the perception of musical tension, that's what we found, mediates its effect on long-term memory. And by showing this, so we can say that continuous musical elements can influence memory formation, and these are possibly mediated by the perception of musical elements, whereas implicit processing of tension enhances memory, and explicit awareness to tension reduces memory. I'll just mention that we have a lot of different types of things that we, together with Shai Gabay and Simon Shamaitsuli, we got this grant of measuring real-life behavior, and we're now using eye tracking glasses to measure pupil dilation within the music processing procedure to see if we can find correlates with a more subtle physiological measurement. So thank you for listening. And I want to thank especially now our school Zoom, who, as I said, is in charge of this project. So thank you. Shahar, should I answer questions or that we don't have time?
Unfortunately, we should move to the next speaker because we are already out of time.
Okay, so afterwards. So we're going on now to hear Aya Ben Yaakov. So the floor is yours.
One second. Okay, thanks, Avi. Good morning, everyone. Sorry, 1 second here. In the talk today, I'm going to be discussing some recent work in which we've been investigating the basic unit of episodic encoding. And in the spirit of the symposium today, I'd like to start by giving you an example of what I mean when I say episodic memory, since I'm interested in naturalistic stimuli, and also maybe because I have a toddler at home. When I think about episodic memories, I may think about things like you'll see in this short film from Inside Out. Now, these are very different from episodic memories in lab settings like Avi discussed. If we try to take the same scenes and represent them in lab settings, maybe they'd look something like this with these brief, discrete stimuli that we're using to investigate memory. And in recent years, there's been this surge of interest in naturalistic stimuli, and it's brought with it new methods for analysis, new understanding. But I think one of the most exciting things is that it brings with it new questions that weren't relevant before when we were looking at these types of simple stimuli. And one of the focuses of the lab at the moment is on one of these questions, asking what's the basic unit that we're encoding to memory. And we're also looking at representation and retrieval, but I'm going to be talking about encoding today. Now, in these simple stimuli, this question is kind of meaningless, right? If we're encoding the sequence, then broccoli is one unit, and then the rubber duck is another, and it's quite clear what the unit of encoding is. But when we transition to continuous experience, that becomes much less clear. Let's say I think back to a morning during my postdoc in Cambridge. My experience was continuous. Yet we know that afterwards, if we look at the organization of memory for that experience in long-term memory, then it's organized in these chunks and these events. So I'll remember I made coffee, then I had breakfast, and then I cycled to work, saying hello to some cows along the way. And then the question arises, when we're encoding this experience, are we encoding every moment in time as we experience it? Or are we encoding these chunks to begin with, these these events that then appear in long-term memory? Now, this question of how experience is transformed to memory, of course, has been studied for a very long time. And there are very influential models that describe how experience is transformed to memory. I think the most influential ones are temporal context models, which are a class of models, according to which we encode every element as we encounter it. So if we have this sequence of items that we encountered, we have some what's called context, which basically includes everything. That can include where you are when you learn this, the state of your brain activity, your emotions, pretty much everything. And the idea is that every item you encounter is encoded, bound to that context in which it appears. So if we're encoding the sequence, we're not encoding any link between broccoli and a rubber duck. Each one is bound to the context. And afterwards, any effects that we see, linking broccoli and a rubber duck are only because they were presented close in time, which would mean their contexts are more similar, and that's why they're more related in long-term memory. But how can these models explain what happens in continuous experience? According to them, if we encounter this continuous experience like that morning in Cambridge, then we'll be encoding every moment in time to long-term memory as we encounter it. And of course, the question arises, if that's the case, how does this experience end up being organized in events? And there are accounts for this using these types of models. And it's been suggested that as we go along with experience, when we switch to a new event, the context changes more abruptly. So one part of making coffee is more tightly linked to another part of making coffee because their context was more similar during experience. But there's still no binding of events. We're still not encoding events as these cohesive units. So why question this? I mean, there's an explanation for how we encode continuous experience. So first of all, inside out gives us a contradicting theory. For those who haven't seen the movie, according to this, we save memory in these little orbs. So when you'll see glowing balls, that means a memory is formed. So looking at the same experience that we saw before, we kind of have these chunks, and every time a chunk ends, every time an event ends, we save a memory. And of course, the reason to question this isn't just because of inside out. I'll very briefly mention the main finding that caused us to suggest a different approach. And that's a finding from quite a while back now, that when we encode continuous experience to memory, in this case, when people were encoding movie clips, we see that the hippocampus, the main region of episodic encoding, waits until the end of the event before responding. Here you'll see there's a stronger response to remembered events compared to forgotten ones in blue. And this response is very late in time. It's elicited at the offset of the event. So the encoding activity at the hippocampus only appears at the end of the event. And you'll see here, if we cover the clip for a moment, this looks like a canonical response, suggesting that indeed the response is to the offset. And this led us to suggest that maybe this encoding activity reflects encoding of bound episodes, that at these boundaries, we save the preceding event to memory as a chunk. And since then, there have been numerous studies, only a few of them here, that have found indeed that the hippocampus responds at boundaries between events, at the offset of events. And more recently, there's been a computational model that suggests that this is indeed the optimal strategy for encoding, not to encode every moment in time as we encounter it, but to encode information in events, to wait until the boundary before encoding. So this gives rise to a different possibility regarding how we transform continuous experience to memory. If indeed we encode bound episodes, then we'll start experiencing something, and then only when we reach a new event, a transition, then we'll save the preceding event to memory as a whole. So the encoding itself takes place, the unit of encoding is an event. And this differs from the account provided by temporal context models, mainly in terms of the basic building block, the unit that's being encoded to memory. And this is what we set out to investigate. I'll describe the first study that we ran to start getting at this basic unit. And we did so using stop motion films. Before I describe the study, I'll show you an example of the type of film that we used. So how can we use these types of films to get at our question? We know from numerous studies that surprise enhances memory. Now, if the unit of encoding is the entire event, we expect that surprise or anything that modulates memory to affect memory for the entire event. And that's what we tested here. So we had these clips, these films, or scenes like the one you just saw, that had a surprising version, like me putting the computer mouse in a saucepan. And each such surprising scene had a neutral version in which the surprising event was replaced by a neutral one, but everything that preceded that and followed that was completely identical. That's why we use stop motion. It enables us to edit the films this way. In addition, each film was preceded by what we called a pre-scene, which was a semantically related scene that was always neutral. And this gives us 4 types of events to look at. We've got our target events, which can be neutral or surprising. We've got pre and post-target actions, which are in the same event as a target one, but they're always neutral. They're always the same actions. And we've got the pre-scene actions, which are across an event boundary. They belong to a different event. We then probed memory for the different actions, asking yes/no questions, both about actions that occurred and about yours. We had 2 groups, one that answered the questions immediately and one after 24 hours, but I'll be describing the combined results now. And there were 344 participants. So how do we use this to get at the question of whether we're encoding episodes as cohesive unit or encoding elements independently? And we're going to be focusing on pre-target and pre-scene actions. If episodes are encoded as cohesive units, then the effect of the surprising target should spread to the entire event, because at the moment of encoding, we've already encountered the surprise. And if it's all encoded together and we know that surprise enhances memory for the material being encoded, it should enhance memory for the event, for the entire event. More concretely, in terms of predictions, this predicts that surprise will enhance memory for pre-target actions, and that if there is an effect of surprise on pre-scene actions, it shouldn't be as strong as the effect on pre-target actions, which are part of the same event. In contrast, if elements are encoded independently, that means the effect of the surprising target should be much more limited to the surprise itself, and specifically that the effect of surprise on pre-scene actions should be the same as pre-target ones. So let's look at the results. And first, just in terms of interpreting the results, this was run using Bayesian analysis. So where it says BF01, that's evidence in favor of the null. BF10 is evidence in favor of the alternative. And anything from 10 and above, something like that, is considered strong evidence. So first, we find evidence against an effect of surprise for pre-target actions. So there's no enhancement for pre-target. And second, there is evidence against an action-surprise interaction. So the effect of surprise on pre-scene and pre-target actions doesn't differ. And this isn't because our surprising actions just aren't memorable or surprising enough, because we see overwhelmingly strong effect for surprise on the targets themselves. So people remember the targets much better if they're surprised. So together, this strongly favors the possibility that elements are encoded independently, in contrast to what we predicted. But then we thought maybe because this didn't match our hypothesis, then we thought of another interpretation for what we found. And that is that surprise may act as an event boundary. The current interpretation is that we have this event, but the effect of surprise is limited to the element itself. Another possibility is that surprise itself acts as a boundary, segmenting our event. So now the pre-target and post-target actions are no longer part of the same event as surprise. And we ran some exploratory analysis to test this, which I'll describe briefly. So we have these scenes, and we're using a measure of dependency that's inspired by work by Aidan Horner and Neil Burgess, And basically what the dependency means is that if elements are in the same event, we expect there to be dependency in their memory. So the chance of remembering a pre-target action should be higher if you remember the post-target action of that same event, and vice versa. And first of all, we verified that this is indeed the case. We look at the dependency between pre and post-target actions for neutral scenes and compare that to the dependency when we randomly pair pre-target actions from post-target actions from different scenes. But now the question arises, what happens during surprise? If indeed surprise acts as a boundary, we'd expect it to reduce this dependency because these actions are no longer part of the same event. And that's exactly what we see. There still is significant dependency for surprising events, but it's reduced, and the difference between neutral and surprise is significant. If we, as a control, look at pre-scene versus pre-target actions, we don't see this effect, although the difference between the differences is not significant. Oh, sorry, this was sorry. Apologies, I'll get back to that in a second. Okay, a trick in the slide didn't end up working as expected. Okay, so to summarize what we found, we see that contrary to our hypothesis, the effect of surprise does not spread to the rest of the event. This supports element-wise encoding, suggests that every element is encoded as it's encountered, but an alternate explanation is that surprise acts as an event boundary, although this dependency analysis is exploratory and confirmatory, and we're planning on running additional studies to verify this. I'll just mention that if anyone is interested in using the stimuli, they're on OSF, and this is just the first step. We're not going to be answering this huge question just with this one study, so there's more to come. And I'll leave you with a take-home question instead of a take-home message. If encoding is element-wise, what's the element that we're encoding? If we have continuous experience, do we encode every single moment? It seems that we would have to have some type of chunking. And with that, I'd just like to thank Verity Smith and Rick Hansen, who collaborated on this project, the members of my lab, and mention that I'm hiring. So if anyone is interested in hiring at different levels, please get in touch if you're interested in joining this work. And I think we have maybe a few moments for questions.
Yeah, we have time for one question. Yeah, Rabah. Hello, it's just a okay.
Okay.
Sarit, please.
Hi. I wanted to ask if surprise could be just disruptive, or is that the same thing as a boundary?
The question is in what sense it's disruptive. I think it could be disruptive in the sense that maybe you orient to that and then you don't notice the rest, and we do see some decline in memory for things that come after. But if it's disruptive in the sense that it disrupts the flow so that now something else has happened, then I define that probably as a boundary.
Okay. Thanks.
So
great talk.
Okay. Thanks so much.
Okay. So now let's move on to Yara.
Okay, hi everybody, good morning. So I'm very happy to be part of this cool symposium on our way towards ecological cognitive sciences. In my case, more in this project, more neuroscience. And before I start, I would like to mention Noa Katabi, who she just finished her thesis in my lab, and she led the project that I'm going to discuss with you today. So I would like to start with a quote that I like by Henry David Thoreau, who said, "It's not what you look at that matters, it's what you see." And I think what he meant by that is that individuals perceive the world through their own subjective filters, through their emotions, their beliefs, their prior knowledge. And in our lab, we're interested in asking, on which level do these filters operate? And I think that a prominent example for such filters are our political views. And it seems that the political realm is becoming more and more polarized. And individuals can watch the same political debate or listen to the same political speech, but actually see and hear very different things. And when elections were declared in Israel in 2019, we thought it's a unique opportunity to test how the political opinions shape the brain response in real time. And specifically, we set out to ask how political partisanship shapes brain activation and synchronization between individuals with similar or opposing political views. To do so, 40 participants, 20 left-wing and 20 right-wing, just 3 weeks before the April 2019 elections, they were lying in the MRI scanner and they watched 8 movie clips. One movie clip was a neutral movie clip, and the other 7 were all kind of contain political content, mainly campaign ads. As you can see here, an example of the left-wing campaign ad that we presented participants and the right-wing campaign ad. And following each of the movie clips inside the scanner, participants answered 3 questions. How much did they agree with the main message of the clip? How much did the clip interest them? And how emotionally engaged did they feel? And this was on a visual analog scale between not at all and very. Outside the scanner, they also filled a detailed interpretation questionnaire on each of the movies. And in the project I'm going to describe today, we analyzed 5 movie clips. The first one was a neutral movie clip about a guy that turned a bus into his home. 2 campaign ads, 1 left-wing and 1 right-wing, and 2 political speeches, one by a left-wing politician, Shahar Arzy, and the other by a right-wing politician, Benjamin Netanyahu. In terms of the behavioral results inside the scanner, the participants' rating after each movie clip, we can see that for the neutral movie clip, in blue you can see the right-wing participants, and in red, no, in blue it's the left-wing, and in red is the right-wing. And you can see that participants were pretty much the same in agreeing with the main message of the neutral clip. However, not surprisingly, this was not the case for the political content, where you can see that there are large and significant differences between the left-wing and the right-wing groups. And although left-wing participants agreed more with the left-wing message and right-wing participants agreed more with the right-wing message, all participants were very much engaged, both emotionally and interested by the movie clips. And I think this demonstrates the power of naturalistic stimuli and naturalistic settings in terms of just before the elections, and in terms of how much participants were engaged, although they did not always agree with the main message of the clip. Okay, so to test for similarities and differences in the brain response of participants while they were watching the movie clips, we used intersubject correlation, which is a method that was developed by Uri Hassan when he did his PhD in Rafi Malach's lab almost 20 years ago. And what we did here is we calculated the correlation of the brain response in each region for each movie within the left-wing participants group and within the right-wing participants group. Then we compared this correlation value to a certain threshold in order to identify regions that were involved in processing the stimulus. Then on the second step, we did a t-test between these two correlation values in order to identify regions that were involved in processing the stimulus only in one group and not in the other. And here's what we got. So for the neutral clip about the guy that turned the bus into his house, we can see these yellow regions that were involved in processing the stimulus in both groups. And we can see some sensory regions, some theory of mind and default mode network regions, some language processing regions. And here are three examples of the actual correlation value, ISC value in the primary visual cortex, primary auditory cortex, and in the hippocampus. And we can see that both groups of participants were activating these regions in response to the neutral clip. What we can see here are blue and red patches, which means that there were no differences between the groups while processing the neutral clip. Now let's move on to the right-wing campaign ad. What you can see here are that in addition to these yellow regions that were involved in processing the stimulus in both groups, there were regions, quite a lot of regions, including regions in the default mode network, such as TPJ or the bilateral temporal pole, and also regions, surprisingly, regions within the somatosensory cortex and premotor cortex that were involved in processing the stimulus only in the right-wing group and not in the left-wing group. And you can see it also here in the bar graphs. And let's see what happened in the other political stimuli. And we can see similar pattern for the left-wing campaign ad, where there were more regions that were involved in processing the stimulus in the right-wing group, uniquely in the right-wing group and not in the left-wing group. And in the right-wing speech, we saw, again, a similar pattern where you can see here that only the right-wing groups, these regions were involved in processing the stimulus only in the right-wing group. And again, it includes some premotor and motor and some other sensory regions. And to summarize only these three stimuli, we can suggest that in the right-wing group, regions that are involved in sensory motor simulated representation, so that right-wing participants used a sensory motor simulated representation to represent the right-wing content. A very different pattern was obtained for the left-wing speech. So what you can see here, again in yellow, are regions that were involved in processing the stimulus in both groups. However, you can see only blue patches, blue regions that were involved in processing the stimulus only in the left wing participants and not in the right wing participants. And these regions included mainly regions within the default mode network, as well as regions in the reward system and some premotor regions. We will talk in a couple of slides, we'll talk about what we think drive these differences between the stimuli. So from what I described till now, it was more about regions that are involved in processing the stimulus in one group and not in the other. But we were also interested in asking whether specific stimuli, political stimuli, are more potent in synchronizing the response of one group or the other. And for that, we used two methods. One was a support SVM classifier on the intersubject correlation value. And the other was a relatively new method, which called intersubject representation similarity analysis, ISRSA. Again, to test whether the more people agreed with each other, the more synchronized their brain response was. And this is what we got. So for the, what we can see here, this is the SVM classifier. The yellowish orange patches are regions where the classifier was significantly above chance, significantly accurate. And the accuracy level ranged from 55% to 86%, which is quite a lot. And what you can see here is that in many different brain regions, including part of the default mode network, such as TPJ or posterior cingulate, but also surprisingly, in the auditory cortex, in the visual cortex, in the premotor regions, we could classify whether a participant is left-wing or right-wing only based on their correlation of the response with the other members of his group. Okay, so we had one value, and based on this value, we could identify whether a participant is left-wing or right-wing. And again, when you look at the here, for example, some regions, you can look at for the right-wing campaign in the right visual cortex, and in red are the correlation values of the right-wing participants, and in blue of the left-wing participants. And you can see that the right-wing individuals were much more synchronized in response to the right-wing campaign ad than the left-wing participants. And the other, the opposite pattern was true for example, for the left-wing speech. If you can look at, for example, the dorsomedial prefrontal cortex, where you can see that the left-wing participants were much more synchronized than the right-wing participants. The second method we used to test for differences in synchronization was the intersubject RSA. And the idea here is to test whether the synchronization differences that we saw on the group level are also true on individual level. So here we didn't use two groups, but rather used how similar were each two participants in agreeing with the main message of the clip. And what we saw here is that stronger views, for example, in the right-wing campaign ad, stronger people that were more similar in strongly agreeing with the main message of the clip were more similar, their neural response was more similar in many brain regions. And again, I want to mention and highlight, for example, region in the visual cortex. Okay, so actually the highest value we got of 0.41, which is very high for this analysis, was obtained in part of the primary visual cortex. And what I also want to mention here is the dichotomy, striking dichotomy, if I may say. So, for example, agreeing with the main message of a right-wing clip generated synchronization in many brain regions, although not agreeing with the message, so agreeing with the left message, did not synchronize the response at all. And you can see this for all, for both campaign ads and the right-wing speech, and the opposite pattern for the left-wing politician speech. Okay, so what is so different in terms of what is unique about the left-wing politician speech? So to try and answer this, what we did is we had another behavioral experiment in which 32 participants, 16 left-wing and 16 right-wing, answered all sorts of questions regarding the 4 political stimuli. And what we saw is that whereas most of the right-wing clip, the left-wing the right-wing campaign ad, the left-wing campaign ad, and the right-wing speech, their main goal was to encourage participants to vote, encourage people to vote, actually. The left-wing speech, the main message, and you see 97% of the participants thought that the main message was to deliver a message, the main goal. Another thing is that when you look only at the left-wing participants, the left-wing campaign ad elicit much more criticism than the left-wing speech, and thus it might be not surprising that the left-wing campaign ad did not synchronize the response of the left-wing participants. Moreover, the majority of the left-wing participants thought that the left-wing speech is the one that represents best the left-wing views in Israel. And again, this may imply that this is why the left-wing speech was much more potent in synchronizing the response of the left-wing participants. So to summarize, what we saw is that differences in the brain response and synchronization emerge already in early sensory, somatosensory, and motor regions. Moreover, we could classify participants' political views based on the level of synchronization with their within-group members. And finally, I think what this project suggests is that political polarization is not limited to higher processes as previously thought, and that individuals are seeing and hearing different things, not just metaphorically, but also literally. And with that, I would like to thank the members of my lab, and especially Noah Katabi, who bravely led this project, and Sharon Yakim, Inbal Ravevi, and Ada Simon that were highly involved in this project. And thank you for listening.
Yeah, we have time for one short question.
May I?
Yeah.
Yara, a very bold study, very nice. I wanted to ask if you, by any chance, checked with the participants what emotions each of these clips elicited in them, and then estimated or analyzed the data relative to these emotions, because these may not be symmetrical. And I also wrote to you in the chat that while I'm quite certain that all of the right-wing participants sympathized with Bibi Netanyahu to a very great extent, I would doubt that left-wing participants sympathize with Tamar Zandberg and Sheli Yachimovich, which are not role models as Bibi is for the right-wing. And I wonder if this emotional, I don't know, synchronization or sympathizes, I don't know how to say that, but anyway, if this may also influence the non-symmetry that you see between the two views, let's say.
Yeah, that's a great question, which we try to answer in the, well, not the emotional response, but the differences between the clips in the other group of participants. What we do have, we have a lot of questionnaires that we ask participants after the scan, and we asked them directly what they think, and they had to rate emotions, different kind of emotions on the political figures, politicians, but not on the clip, because it was, yeah, it was already a really long scan, but so we can't use synchronization because we have only one value. And not dynamics over time. But what I can say that, at least in terms of how much they agreed with the main message of the clip, or afterwards when we asked them memory questions about what happened in the clip, or interpretation questions, it didn't seem that behaviorally the left-wing participants were less synchronized than the right-wing. So, and also, in terms of the population, the left-wing participants were much more homogenic. So it was
Mhm.
almost only Tel Aviv University students, which were merets, and the right-wing participants were much more heterogeneous. And as you can imagine, Tel Aviv University is not very representative.
Yeah.
And so this surprised us. I mean, it's the other way around. But
So
I totally agree with the intuition.
So just I want to suggest, if it hasn't
we
been
are out of
published.
time.
Okay, I'll write to Yara
So
privately.
if you can,
Thanks.
I apologize.
Thank you.
But I have also to respect the last speaker, which is actually myself. So I'm happy to conclude. I'm happy to conclude this session. Miracles. You see my screen? Good. Thank you. Each time when I go to a conference and I see these Ekman faces, actually maybe the only emotion that is evoked is some kind of an anger or like what I did wrong that I should see these faces again. I'm not feeling like moved or something by this emotion. Like, for example, this woman, when she went to see immigrant children in some kind of prisons, say to the world that she doesn't really care. However, even this woman, when she saw this poor guy standing wherever he stands, probably was very proud and happy. What I'm trying to say is that when we say as the Ekman faces, we are mostly influenced by the tasks that we have to do. The stimuli are not touching us very much. However, if we see a dear one, so whatever the task is, we are first of all moved by his or her or her appearance and to a much greater extent. And that's why I would like to preach even in this short talk and the sessions that we should use such stimuli instead of or approach instead of the old Ekmans that even their validity is doubtful. At our lab, where we apply this approach to life itself. And what is life itself, or where life happens? It's like mostly the spatial world where we live and act, our own historical autobiography, and people in our social network. There are other domains, like, for example, our political views, as Yara beautifully showed. But I guess these are the three main ones. And we follow as a basic definition of what we call orientation. Is like the relation between ourself and the imagination, or the presentation of these three aspects of world: the space around us, the events of our life, and people with whom we share these events and give rise to our autobiography. In the 15 minutes that I have, I would like to present very briefly three different stories. One is how does the use of one's own social network, here from Facebook, teach us about what matters in friendship. Very, very briefly, I will just mention the a poster that Moshe Rosman from the lab will present tomorrow. Where should we put our social energy? A view from the brain. And finally, what does this have to do with Alzheimer's disease? So let's start. So this is a Facebook network of a real person. And with a tool that is called Lost Circles, one can map the connectivity within this network with the permission of the user, and the clusterization according to the connectivity to different groups. And this is this was done by Michael Peer from the lab and was published in in Journal of Neuroscience several months ago. So what Michael did in this work is first segment totally in an objective manner the Facebook network of each participant, and then under fMRI he presented the 24 different people from one's social network and asked different questions about these people. And the original intention of us was to evoke and the image or representation of these people and see how the social network that is represented in the brain is correlated to the objective social network as it is in Facebook. And we asked questions from three different categories. One about personal affiliation, for example, how much do you trust or like this person? One about personality traits, how funny is this person, how charismatic, and one about appearance, how pretty, how tall. Now, we use the RSA, which is a method that I'm in love with because it really like connects the rich behavior with